everyone. I would like you to welcome to the course on lithium-ion battery pack design considerations. And as you know by now, where EV has become a current trend and it's going to be the future of the mobility, where lithium-ion battery pack is the most important power source of the whole electric vehicle, which makes the whole focus on lithium-ion battery pack to be safe. It has to be robust enough to handle a lot of shocks, vibrations, etc. So this course will be mostly focusing on those considerations needed for a very good battery pack design. So since this is a very huge topic, we'll have this whole course split it into 3 different weeks, and sessions of this week would mostly focused on lithium-ion battery pack design considerations, cell basics, cell sizing, selection of cells, what are the different form factors available, what are the different chemistries that lithium-ion has, etc. And also we'll also have certain sessions where we'll also focus on what is the right cell selection for making a pack, because each application has its own needs and we'll have to choose the right cell, which is the most important part. So we'll get into the table of contents. So this session would mostly focus on lithium-ion cell chemistries, what are the form factors of the cell, what are the different cell configurations like series combination or a parallel combination or a combination of both, which are needed to make a module. And then we'll also focus on what are the factors needed for selection of a cell, and then we'll have a case study followed by that to understand what do we need to do to select the right cell. Then we also get into understanding of how to design pack, which is from cell to module to pack. We'll also understand what's the process involved in that, and then we'll also have a subtopic where we'll have to understand what are the considerations for design of a module. So since we have different form factors, we'll understand each form factors design considerations for the module, and then since we concentrate on the case study, that leads to more elaborated understanding of prismatic cell module design also. And also we'll understand what are the different components in the battery pack, what are its roles in the battery pack, what is important, how does it play a vital role, etc. And what are the robust pack requisites, because battery pack being the whole power source, it has to be handled safely. So what are the most important aspects that it has to sustain, it has to withstand loads, shocks, vibrations, thermal loads, temperatures, etc. And then we'll also understand what are the wiring harness designs, what are the power cables used, because power cables being the primary source for transferring the electric current from the cells to the motor. We'll also have to choose the right cell and also a right power cable. So we'll also understand what does that mean. Now when we go to the learning objectives, as we saw in the previous slide, this would be the objectives of this session for this week, which is mostly where we'll understand on what are the operating voltages of lithium-ion cells, what are the different form factors, different sizes, different shapes of lithium-ion cells, and also what is the right cell selection for the application, which is basically based on the C rates. We have an EV which is working at 1C or 0.5C, etc. So this is something which we hear quite often. So we'll understand what are the C rates, and then we'll also understand what are the capacity of the cells, packs, modules, what are the cell sizes available in terms of dimension, in terms of capacity, etc. What are the vehicle volume, which is like if there is a space, in that space we need to fit a battery pack. Is the space sufficient or not? If it's not sufficient, how do we make our battery pack such that it goes and sits in that place? So vehicle volume plays a very important role. So we also need to see that when we select a cell, it is compact enough to fit into that vehicle volume. And then we'll also understand what are the motor nominal and peak ratings, and according to that, how do we size our battery pack. And then we all focus on what are the series parallel combinations of modules, because module consists of cells and battery pack consists of modules. So we'll have to make a right combination of cells in series and parallel to get the right battery pack specification in terms of voltage and capacity. And what is the process of conversion from cell to module to pack. And this lithium-ion battery pack, when we say, it is a combination of lot of components which are electrical, mechanical, electronics, etc. And each component has its own purpose, has its own role. So we'll also understand what is its role, what are the different components involved, which would give a fair idea of what is its need and how does it help in the whole battery pack design. So we'll move to the course introduction. So, as you know, this course mainly focuses on design procedure carried out from selection of a cell to making a battery pack. So the different process steps involved in designing a module, which involves like thermal designs, and mainly thermal is one of the most important part. So when we have a cell, there is not just one cell available. There are different types of cells available, and selecting the right cell for an application is something the most important task for a battery engineer. So this course would help you, in realizing what parameters are to be looked at in a cell data sheet and choose the right one. So we'll also have a good emphasis on electronics, wiring harness, which would include different types of sensors, BMS architectures, high voltage, low voltage, how BMS architecture looks like, what is its functionalities, so what is the performance of battery pack, what are different assembly processes involved in cell to module making and then to pack. So not just that, we'll not limit over there. We'll also understand what are the different kinds of ingress protections needed to make sure that the pack is sturdy. And ingress protection is something like a foreign object like water or dust enters into it. So that is also a most important part for a battery pack design. We'll also understand those aspects of the battery pack, and we'll also understand the thermal aspects of the battery pack. Like if there's a cell, if it is discharged or charged, there is a certain amount of heat being generated, and it's very important that has to be removed. So we'll also understand what are the thermal loop designs for a battery pack. So this course would concentrate on everything that is needed for a battery pack, right from cell selection till the whole assembly process. So let us get into the course now. So before that, let us have a small idea on what are the prerequisites for the course. So this course would be interesting, and if you already have some understanding on different lithium-ion chemistries, electrical wiring, electronics, that knowledge would definitely help you in giving more interesting aspects on this course, how it's going to be. Or else nothing to worry about, because this course, as we go on through the slides, each and every basic are already been touch base, so you'll understand it very easily, so shouldn't be a problem. But what are the main skills required is like there has to be a certain level of understanding on what are the different lithium-ion chemistries, a little bit of knowledge on electronics, electrical, basic knowledge on the relations between current, which is basically Ohm's law, current, power, resistance, voltage, etc. A little bit of knowledge on thermal studies like thermal conduction loss, convection, radiation loss, how do you calculate the heat generated, etc. So this is basically a cross multi-domain functionality course. So nevertheless, we are going to touch base on every topic, and wherever there is a need of any basic behind it, we'll definitely cover in that. That is being covered in this course of sessions, which will help you in understanding what is it, how is it happening, and why is it happening. So there's nothing to worry about that. So now we'll go to the course, which is the first topic, which is lithium-ion form factors in chemistries. So when we say lithium-ion form factors in chemistries, form factor is nothing but how does a cell look like in terms of sizes, shapes of the cells, etc. Usually when we say lithium-ion battery pack is the bigger one. So battery pack consists of cells. So that is this cell. So when we say lithium-ion cell, it is referring to just a cell, which is this cell, or it's a cylindrical cell, or it's a pouch cell, or a prismatic cell. So mostly lithium-ion cells are in 3 different form factors throughout currently available, which is cylindrical cell, which is pouch cell, and prismatics. So apart from these 3 cells, there are also coin cells, which you might have seen in your wristwatches, tiny small cells which are circular in shape. But small cells means smaller capacity. Hence, when we have to use it in EV, an EV needs a lot of capacity, a battery pack. And when such cells are used, you need to combine a lot of cells to be added in parallel, which will give a huge resistance of welding when they are welded together. So it makes it quite difficult for the manufacturers when such tiny cells are used. Nevertheless, but these small cells are used in the R&D labs by the electrochemists to conduct small experiments, because making such a big cell would be time consuming, would be a lot of energy has to be put in, a lot of money has to be put in, which for the R&D purpose, which is not feasible. So small cells are used for this one. So basically we have these 3 cells, cylindrical, pouch and prismatic cells, which is majorly used for EVs. And then when we say cylindrical, pouch and prismatic, each cell has its own advantages and disadvantages. For example, Tesla uses cylindrical cell, BYD uses prismatic cells. So why do they use in each cell? Because it is their flexibility of design, it's their easiness with that technology which is being used. So when we say a cylindrical cell, basically cylindrical cell has been commonized throughout the world right now, and has been commonized so much that throughout the world there is only some formats being used, like 18650, we have 2170, 3270. So when we say 18650, that is related to a cylindrical cell, and when we say 18650, 18650, the first two digits, which is 18, resembles to the diameter of this. And when we say 65, 18650, which is the length or height of the cell. So that is the cylindrical cell dimensions when we represent it as 18650. Similarly, when we have 2170, the first two digits resemble the diameter, and the next two digits, which is 70, resembles the height. Similarly, we have pouch cell and prismatic cell, and these are not yet commonized because these are cells with much more higher capacities. So that's the reason this has not yet been commonized. But when we talk about the form factor, we have cylindrical cell, which all has a shell of a cylindrical shape, and which is mostly an SS or a nickel. And when we have pouch cells, which is the second one, if you see, this is quite thin, and the cover or the enclosure used is a aluminium foil. This cell, pouch cell, is able to hold a lot of capacity compared to a cylindrical cell. A cylindrical cell can have typically up to 5 Ah capacity, whereas a pouch cell can hold up to 60 to 70 Ah of capacity, which is way high than what a cylindrical cell can hold. Same is the case with the prismatic cell. A prismatic cell can hold a capacity of 200 Ah. And if you see how much of the capacity is held in prismatic cell, it is way higher than the cylindrical cell. But the common difference you might have noticed over here is prismatic cell has a shell which is like 0.8 mm thick. Aluminium can is being used for a prismatic cell, whereas for a pouch cell, a thin aluminium sheet is being used for this. That makes the name, which is pouch cell. It's a pouch-like structure, or the membrane is being used to enclose the whole pouch cell, whereas the prismatic cell uses a can, which helps in its own structural rigidity, whereas pouch cell has a little bit of a disadvantage there. So this is how the form factors of a lithium-ion cell is. Cylindrical, pouch, and prismatic each has its own advantages. Cylindrical cell being small, it can be flexible. You can put it in any direction, any orientation, any shape. Pouch and prismatic cell are mostly common. You can arrange it in only rectangular ways because of its shape and the nature of its cell. Now let us understand what are the lithium-ion chemistries. So one common myth is like lithium-ion, not many people understand. Like when you say lithium-ion, it's a common chemistry, it's a single chemistry, but no, like lead acid or nickel zinc. No, lithium-ion is not like that. Lithium-ion itself consists of a lot of chemistries. Like we have lithium iron phosphate, LFP. And then we have nickel manganese cobalt, NMC or NCM. And then we have lithium titanate oxide, LTO. And then we have lithium polymer, LiPo. So just to touch base on how a lithium-ion cell is constructed, we know lithium-ion, any cell will consist of a positive and a negative anode and cathode. So this chemistry which we talk about, LFP, NMC, LTO or LiPo, are the cathode components of a cell, which is the positive. And the anode is going to be mainly a graphite or a carbon, which is the anode, which is the negative element. And both cathode and anode are separated by a separator, which is a thin membrane, which is a nano-sized membrane which allows the ions to flow across. And that's how the ions pass through the membrane, which is called a separator between anode and cathode, and that's how the charging and discharging process occurs. So when we say that the cell has been short-circuited internally, which means the separator which is being used has been punctured because of these ions passing. So that is the reason we say the cell has had an internal short circuit and the cell has failed. So basically a cell is a combination of a cathode, anode and a separator, etc. And each material used for a cathode like LFP, NMC or LTO will have its own electropotential voltages. So that's how the whole chemistry changes the whole voltage window of a lithium-ion cell. For example, each chemistry over here has a different voltage window, and this combination of materials in a cathode also determine the energy density, also determine the C rates, also determine the life cycles of the cell, etc. So these are the initial cathode components which are playing a vital role in selection of a cell as per the application. For example, LFP, lithium iron phosphate, has a higher life cycles when compared to NMC, but it cannot give higher C rates when it compares to NMC. Similarly, lithium titanate oxide, it has higher life cycles, it has higher C rates, but it is way heavier than what an LFP or NMC is. So it's all based on chemistry materials, based on cathode materials and their respective phenomena, which are unique for their own, and it has to be based on the selection it has to be chosen. Now we'll understand what are the different form factors and its advantages and disadvantages. As we now understand that there are three different form factors, which is cylindrical, pouch and prismatic. And we also saw how the construction done. Cylindrical cell is basically done in a can. Pouch cell is using a pouch foil as an aluminum enclosure, and prismatic cell is basically in a steel can. So because the constructions, the process of manufacturing involved are completely different, each cell has its own advantages and disadvantages. So mind you, I would like to remind you that cylindrical cell is a cell which is having lowest capacity. The maximum cell capacity possible is 5 Ah currently, and then we have a pouch cell which has a decent capacity, it can hold like 60 Ah or 65 Ah, and then we have prismatic cell which tops the whole list, which can hold up to 200 Ah also. Now when we talk about advantages and disadvantages of these form factors, which are the primary motives for selection of a cell with respect to form factor, when we have a cylindrical cell, cylindrical cells are basically available in all small sizes, as we see, like 18650 and 2170, which means 18 mm dia and 65 mm height, which is a quite small number. Being at a small size, it helps in flexibility of arrangements in series and parallel combination. So this is something where you can orient it in any direction so that you can get the required capacity. It's just that you will need more number of cells in series and parallel combination, but when you have space, when you have the flexibility, you can do it in either ways. So that is one thing which the cylindrical cell users take advantage of, primarily being Tesla. It's the only car manufacturer who uses cylindrical cells, and that's the advantage which they see in it. And also another advantage of this is cylindrical cells have a cylindrical can, which is of Tickle or SS, anything. And if you go into a little bit of basics of mechanical engineering, you could identify that a cylindrical object or a cylindrical shell will have a higher Hoops stress against internal stresses. Since the cell is tend to charge and discharge, there would be always an expansion and contraction in the electrodes, which will allow the cell to expand and contract, which means after a certain point of time, when after 10 charge cycles or 100 charge cycles or 200 charge cycles, when you suddenly see, you might have observed the cell is little bit bulged, and that you cannot see in a cylindrical cell because of its nature of construction having a cylindrical can around it. So that is one of the reason why cylindrical cell has an advantage, where other cells like pouch cell, prismatic cell will require a lot of pressure plates, thermal foams, etc. to hold that kind of expansion, whereas cylindrical cell will not need it. And when we go to the disadvantages, if you see the cylindrical shape, because ultimately when you make a battery pack, it has to be in a square or some kind of form. Since the cylindrical cell is round or circular in nature, if you take a square and you fit the cylindrical, all the four corners are the loss of areas. So those areas, when you put a lot of cells together, you will have a loss of required area. So that area is not being filled up. So unless you use a phase change material or a thermal dissipation material and fill it there, it's of no use currently. So that is how you lose area while using a cylindrical cell. And also you also have a challenge in extracting heat from the cells. So because there is no flat surface anywhere in the cylindrical cell, the way you extract heat from the cylindrical cells becomes quite difficult. And then you have pouch cells. So pouch cells, as we discussed, like pouch cells are available in very big capacities like 50 Ah or 60 Ah, so which is not the case for cylindrical cells. Now, for example, we need a 50 Ah capacity with a single pouch cell. Whereas if we want to do that with a cylindrical cell, we'll need to have 10 cells of 5 Ah put in parallel together. So when we do that, when we are paralleling the cells, there are bus bars used for connecting one cell to another cell in parallel, which means you'll have 10 interconnections. 10 interconnections, each weld joint will have its own internal contact resistance. I would say, contact resistant that would add up to the heat. Instead, if you use one pouch cell, it makes the whole job easy. So that is how you have a great advantage with pouch cells. And then another big advantage is heat dissipation. Unlike the cylindrical nature of the cell, you have a pouch cell which has a flat area, and when you have a flat area, you can put any of a conducting material or a heat sink over there, and you can extract as much as heat possible from that. So that is one of the great advantage that you have with a pouch cell, because it has a large area, and since the capacity is high, it tends to generate heat, and that heat could be easily removed from the cell. So that is one advantage, and because of its high weight, and also a very thin enclosure material is used around it for as an enclosure sheet, which makes the cell a little bit lighter when compared to SS can or aluminum can for prismatic cell. Hence you get higher energy density, which is watt per kg. Now this is how you get some benefits in pouch cell. But it's not just that. Now, each cell will have its own disadvantages also when compared to advantages. That is, when you put some 10 or 20 pouch cells together, this pouch cell has a very thin enclosure material, which is a foil, and it tends to expand over a period of time. When that expands, you will need a lot of pressure plates to put across to hold that expansion, which could be thermal foams, which could be cell holders, which could be heat carrier plates. You put everything across a cell, and then you tighten it very hardly against the torque. Like this values of torque for tightening and applying pressure on the cells is completely achieved through a thermal simulation. By understanding the cell testing or physical testing has to be done on the cell, and those values are used for the structural simulation to understand the expansion, and those values are taken to put the reverse pressure on the cells so that you can hold the cells against expansion. So when you see that, there's a big process involved, and it would definitely expand over a period of time. And also, to hold that kind of expansion, you will need a lot of components required, and that makes the whole process complex. And then we have a prismatic cell. So prismatic cell is even more capable of holding much more higher capacities. And since this is a shell, it has an aluminum can, and the whole electrodes, cathodes, anodes, separators are put in that. The module design becomes easy because each cell itself holds a higher capacity. And unlike the pouch cell, now if you see, we have a pouch cell and we have a prismatic cell. This prismatic cell is thicker than a pouch cell. So which means this doesn't expand like how a pouch cell expands. So you don't need a lot of pressure plates and a lot of holding materials for a prismatic cell as compared to a pouch cell. So that makes the whole design a little bit easy. And then one disadvantage is sizes. Prismatic cell is very big in size, and when you want to use prismatic cells with such high capacities, you definitely cannot use it in a two-wheeler. So that is one of a problem. Either you'll have to design a customized two-wheeler prismatic cell for a small size so that you can fit it in a two-wheeler, or else high capacity prismatic cells can never go in a two-wheeler bag. And then another disadvantage, or it could be a challenge, is usually prismatic cells can be welded. I mean, one cell to another cell. When we want to connect one cell to another cell, there are different ways to do it for a prismatic cell, which could be a laser welding, or you could tighten them with a nut and bolt. So when you use such kind of nut and bolt system, the contact resistance between the bus bar and the cell is a little bit challenging. It is high when compared to a very good weld joint. So that is a challenge that you would face in the prismatic cell. Now we talked about flexibility of the cylindrical cells. Here we would see how the flexibility of the cylindrical cells can get affected and what are the advantages in those arrangements of the cylindrical cell. Now first one is a straight arrangement. We could see all the cells are arranged one beside the other. Now when I said there's an area loss, I am talking about this area. So this area is nowhere to be filled. Now how effective we put the cells, we reduce the gap between each other and even the package it. This is some area which you definitely lose in common. So to avoid that, you could do a zigzag arrangement where some of its area has been utilized, but still you have certain voids formed between the two rows or three rows, etc. So that is how you will find that there is some loss in area when it comes to cylindrical cells, whereas when it's in pouch and prismatic cell, because of the rectangular nature, you won't have such voids of spaces forming. Now we would enter into lithium-ion voltage chemistries. for different voltages and its chemistries, etc. So the whole lithium-ion voltage window is divided into three different types. We have a nominal voltage, which is also called as open circuit voltage, which is like when a positive and a negative electrode are put together, there is a certain potential which happens to be there, which tends to give a nominal voltage, also called as open circuit voltage, nominal. And then we have a maximum voltage, and then we have a minimum voltage. So maximum voltage is the voltage when you fully charge the cell, and that is how you reach a maximum voltage window. And minimum voltage is when you fully discharge the cell, you reach a lowest point of the voltage window, that is called as the minimum voltage. And when we have different chemistries like lithium iron phosphate, nickel manganese cobalt, lithium titaniate, lithium polymer, each cell has its own voltage window. Now here we see LFP, which has a nominal voltage of 3.2 volts, and then we have a maximum voltage of 3.6 volts and a minimum voltage of 2.5 volts. Which means when you have a cell and it is charged to a maximum voltage of 3.6, it can be discharged to 2.5 voltage. We have NMC, which has a nominal voltage of 3.65 or 3.7 volts, and when it is charged, it can reach up to 4.2 volts, and when it is discharged, it can reach up to 3 volts. So which means the working window of these cells are basically from 2.5 to 3.6 volts for LFP, 3 volts to 4.2 volts for NMC, 1.5 volts to 2.8 volts for LTO, with a nominal voltage of 2.3, and lithium polymer is somewhat closer to what a nickel manganese NMC cobalt cell is, which is similar, almost 3.7 volts. When charged, it goes up to 4.2, and when discharged, it comes up to 3 volts. So this is the voltage window for the lithium ion polymer cell. So these are all chemistry voltages are all dependent on the cathode materials which are being used, and these are certain values which are quoted as per generalized values. Usually it depends also on the OEM till what extent they can provide. For example, in some OEMs or cell manufacturers can give a nominal voltage of 3.55, and they say that they can go up to 2.8 volts, which is when discharged, it can go up to 2.8 volts. So it depends, it changes from cell chemistry to cell chemistry or the material composition being used, whereas NMC is going to be the common, but there could be some additives or some dopants which are going to be used, which makes this kind of changes. So that is some secret ingredient which they add to have some advantages, like it can allow higher C rate operations, or it can allow operating at higher temperatures, or it could lead to increase in the life cycles. So there could be multiple factors why this open circuit voltages or the maximum and minimum voltages can differ, but it is done with a certain intention to get some advantages out of it. Now we'll understand what are the different cell configurations, which is how the cells are arranged in series and parallel combination to make a module. Remember, a module is a combination of cells which are arranged in series and parallel. So let us go through that. Now here we have a table where we can see different combinations: 12S1P, 1S12P, 6S2P, 2P6S, 4S3P, 3S4. Now we have a cell configuration slide where we have 12 cells in a module with 3.7 volts and 50 Ah capacity of a cell. So if you see 12 cells, we have different combinations or series and parallel configurations formed, which is like 12S1P, 1S12P, 6S2P, 2P6S, whatnot. So what does this mean? This means, as if we refer to the basic formula of Ohm's law, which is V is equal to IR, which says if we connect n number of cells in series, the voltage adds up. If we connect the same n number of cells in parallel, your capacity builds up. So we are following the same formula over here. It's just that a module has 12 cells and we are going to connect 12 cells in series, which will lead to 44.4 volts for a module. And we have each cell capacity being 50 Ah, and since there is no parallelization, we have 50 Ah for that. Which means the module of 12S1P configuration will have 44.4 volts and it will have 50 Ah capacity. Now similarly, if we have a module with 1S12P configuration, we will have a module with only 3.7 volts, but the module capacity will be 600 Ah because 12 cells are connected in parallel. Similarly, if we see 6S2P, which means we have 6 cells connected in series and 2 cells connected in parallel, which will give 22.2 at module level voltage, and will give 50 Ah times 2, which is 100 Ah of module capacity. So that's how You can try different combinations in a same cells module. Unless you have two modules or different voltages, you cannot connect that, because high voltage and low voltage can always have a potential difference, and the voltage would always flying from high voltage to lower voltage. So when we have to connect multiple modules in series, it's to be important that all the modules have to be of same voltage and they are to be connected in series. It's easy in that way. So that is how we have different combinations arranged at a module level. When we have n number of cells, they have to be carefully selected in series and parallel combinations, so that you connect all those modules together to get the right pack voltage and capacity. Since we have understood till now what are the different form factors, what are the different lithium-ion chemistries involved, what are the advantages and disadvantages of the form factors, and how the module configurations are done, now we'll understand what is the driving factor for the cell selection, what are the important needs for selecting the right cell. So here we have listed down a few factors for a right cell, which is like, if you want to select a right cell, we need to have the following factors, like motor rating. What is the continuous and peak current requirement, and what is the operating voltage window of the motor. Motor ratings are something which drive the battery pack specifications, like in terms of pack voltage, which means the battery voltage should be maintained within that motor voltage window throughout the drive cycle. Or else you can see sometimes the motors or the fans at your home run at a very slow speeds. It's because of low voltage. The same would happen over there also. It's a daily life application example which you'll find. So the motor rating and the motor voltage window should be at least equal to that of a battery pack voltage window. So that has to be considered first. And then we have target range, vehicle's target range, which is how many kilometers that the vehicle has to achieve in one charge cycle, which is basically deciding on the capacity of the battery pack. If you have a higher capacity, the more kilometers you can get. It is like the petrol tank in IC engine vehicle. The bigger petrol tank you have, you can travel longer kilometers. It is the same. So that is how you decide on the capacity of the battery pack. And then once all these like battery pack voltages, battery pack capacities are decided, then the most important part that you need to understand is the vehicle C rate requirement. What are the vehicle C rate requirement needed over here, which is for accelerating the vehicle, which is when you want to overtake, when you want to go at a certain speed or higher speeds, what are the C rates required. And this doesn't only require, when you say accelerating, which is called the discharging current, and when you say accelerating and moving faster, it becomes peak current. So there are different kinds of C rates, like continuous current, peak current, and this is for both charging and discharging. So when you say continuous current is something when the current is quite stabilized, when you're going on a flat road and you're going at a normal speed of say 45 kilometers per hour or 50 kilometers per hour, where you're not interested in overtaking some other vehicles, you're going at a pace. So that is how, which is called as a continuous current. So you don't draw a lot of current over there, which is called as a continuous discharge current. But whereas when you want to go somewhere quickly and you want to accelerate many a times, which is dependent on the motor's capability and also the battery pack's capability, and that has to be matched often. So that means if the motor is capable of taking more power, it's capable of delivering more thrust to the vehicle, but the battery pack is not designed for it, you need to really look into that. You stop saying that this battery pack is capable of giving only this much, I have only this amount of power that can I offer, and don't ask me for more. So you will program this in the BMS saying that this is my limit and I could give only to this, and the motor will deliver only that. So that means your motor would be highly sized and your battery pack is not going to deliver such C rates. Then the whole performance of the vehicle goes down. So you'll have to understand what is the C rate of the motor, what is the capability of that the motor will deliver, and there is a real need that or not, and then you choose the right cell for that application. So that is how your peak C rate comes, peak discharge rate. So whenever you're moving on the vehicle, everything that you are doing on the vehicle in motion is going to call, and when your vehicle is stable and you put on a charger, that is called a charge current. And C rate is something which is associated with that. How fast you want to discharge, how fast you want to charge the vehicle is nothing but C rate. So this is how the whole C rates have been arrived at. Like it's called a continuous C rate, it's called as a peak C rate. So basically charges currently in India are continuous C rate. So you fix the charger to the vehicle, it will be charged at a continuous rate. It's a standard rate. So whereas when you say discharge, it's always dynamic. You cannot expect a single C rate or a single rate at which the discharge would happen, because it's a road. You will accelerate, you will decelerate, you will brake the vehicle, etc. So that is how your C rates are important. So that plays a vital role in selection of the right cell. So another important feature that you will have to take care is the life cycles and operating temperature of the cells. So one charge and discharge cycle is termed as one cycle. So which means when you say one life cycle, it has completed one charge and one discharge together. So this life cycles of the cells, like they are decided on how many number of charge and discharge cycles you can deliver when you reach to a capacity degradation stage. In simple terms, like the working life of a cell has been exhausted. So typically for EV applications, when they degrade to 80% of their capacity deterioration, you put out the cells from EV. You don't use it for electric vehicles anymore. You could use those for storage or any other applications, because after 80% of degradation of this capacity, they won't be able to deliver such high C rates like 1C, 2C and 3C. So here I would like to give a little bit of emphasis on what is the C rate and all, which I think you might be more curious to understand. But you would come across those items of C rates and etc. in the next coming slides. So let us now stick to the driving factors of the cell. So also the life cycles are defined at continuous C rates only. So which is a standard C rate. Life cycle is always designed at a continuous C rate, which is like you're not abusing the cell too much. It's a safe operating condition. It's continuous C rates are always the safe operating conditions, and life cycles are always defined at the continuous C rates only, and also at optimum operating temperatures. So this is how a cell is defined at. So when the cell is rated at 0.5 C or 1 C rate, the life cycles say are 3000. That means if you're going to charge and discharge the cell at 0.5 C or 1 C, then only you'll get 3000 life cycles, or not, you will not be able to get those kind of life cycles at all. So that is how the life cycles of a cell are arranged. And then one more important thing is vehicle fitment, space and location. So the battery packs on high voltage battery packs like trucks, cars, etc., they can be mounted on the chassis, they can be mounted on the rooftops, they can be mounted anywhere. So knowing where that location is, how that placement is going to happen, how are they mounting the battery pack is something very important to know, because that will give you an idea of what would be the vibration loads over there, what would be the kind of environment that's going to be, like it's going to be too much heat, because if it's on the chassis, there will be a lot of radiation coming from the roads. So your pack is going to experience extreme load conditions, not just the internal heat generation, but also from the road radiation. If it's on the rooftop, you will be absorbing all the heat that is coming on the top of the vehicle. So that vehicle location is also where the battery pack is mounted. Its location is also really important to know. And then we have vehicle fitment space. As we discussed during the form factor slides, we know different cell form factors have different advantages and disadvantages. When we say about vehicle fitment space, now as we discussed on the form factor slide where we have cylindrical cells are usually smaller in size and there's a lot of flexibility in arranging them. But whereas when we have pouch cells, prismatic cells, they are bigger in size. So that is something where it becomes very important to choose the right cell depending upon the vehicle fitment space, what is the dimension of that available space available, and whether you can accommodate all the cells in that space or not. Remember, it's not just the cell which you'll have in a battery pack. You'll have a lot of other components, like you'll have cooling plates, you'll have BMS, you'll have a lot of contactors switching air over there to prevent the battery pack from high currents, high inrush currents, etc. So it's not the cell which is going to be in the battery pack. There are a lot of other components in the battery pack. You'll have wiring lines, you'll have voltage sensors, you'll have current sensors placed, you have power contactors, etc. So it's important to consider all those things, and then you decide on the cell so that you have a proper vehicle fitment when the whole battery pack has been designed.